Alrighty, so we're going to be looking at the diagrams on the right here in order to answer the questions on the left. So number one wants to know which diagrams on the right would we consider to be elements. Alright, so the way it's going to happen is I'm going to read the question. I want you to pause when I read the question, or after I read the question. Try to answer on your own, and then hit play so you can check with myself. It's the best way that you can learn these. I don't want to make you have to go through two Edpuzzle videos, so this one will not be an Edpuzzle format. Alright, so number one, elements would be A, C, and D would all be examples of elements. Alright, number two, which diagrams would be elements made of single atoms? Alright, so you might want to pause now so I can give you the answer then. Alright, and the elements made of single atoms would be A and D. Right? In our picture for C, I know they're not perfectly touching, but we're trying to depict diatomic molecules there, or diatomic elements. Alright, so number three, which one has elements made of molecules? Well, that would be C, our diatomic element, right? That would be something like oxygen or nitrogen or hydrogen that in nature we find two atoms bonded together when they are out and about. Number four, which ones would be examples of mixtures? B would be a mixture, E, F, and H. So B, E, F, and H would be mixtures. Which ones would be compounds? Which ones would be compounds? That would be G. G is a compound. Number six, which would be a mixture of two compounds? Alright, that would be B would be a mixture of two compounds. And number seven, what would be a mixture of two elements? Well, that would be E and F would be our example, right? Not H, because H actually has three different types of elements. Alright, so hopefully you paused video during the activity, or else it was probably just really weird watching me read these off super fast. But you will be seeing questions like this in activities and on your Unit 2 test as well. Right? These diagrams depicting of what our particles look like are very important. Alright, moving on. Alright, so we're going to be starting to talk about, I'm going right back to the top right now, talking about our different types of mixtures. So you'll want to have your Unit 2 packet out and open to page 20. Now, the first couple slides are not going to be part of your notes, but make sure you're paying attention. So, right here we have two diagrams of mixtures. Right? We can break mixtures down into two groups, either the heterogeneous mixtures or the homogeneous mixtures. Heterogeneous mixtures look like they're made of different things. They're not uniform throughout, while homogeneous mixtures make it look like it's made of one substance, and it looks uniform throughout. So, if we're looking at like the particle view here, right, imagine it's like a piece of granite. We have one colored substance here and then another different colored substance up top. We can definitely see how there's not a uniform pattern. Now on the right here, there's no chemical bond between our purple and our green atoms here, but they are staggered in a uniform shape, or there's a pattern here. Right? So this would be a homogeneous mixture. So even though there's no chemical bond or chemical change taking place, right, it looks uniform throughout. And some real world examples of these, right, a homogeneous mixture would be something like coffee. It looks like one uniform substance throughout, even though we know it's just our coffee grounds have dissolved in the water. Right? There's no chemical reaction taking place. While a heterogeneous mixture might look like our closet full of clothing, right? We have different colors and different shapes, right? Nothing looks uniform throughout. The uniforms are not uniform. I cracked myself up. Alright, and then this is something that you might have seen on your homework question from last week. It asked you a question about motor oil, and how could we tell that motor oil was a mixture? And one of the things that gave that away is that we have different types of motor oil, just like we have different types of milk. Right? So hopefully you're a normal person like me that drinks 2% milk, but if you are a strange one that drinks either 1% milk or skim milk or whole milk, right? These different types of milks show us that we have a mixture, because we just had to add in different amounts to get a different product, right? And you might even notice on your milk, right, that there is the word homogenized here. So when we first get milk from the cow, it's not as smooth as when we get it. It's actually pretty clumpy. So luckily they mix it together really well. They homogenize it so that it looks uniform throughout. Could you imagine drinking milk that was not uniform throughout? That would be disgusting. Alrighty. Alright, so let's get into the notes here. We're going to be starting at the top of page 20 with your solutions. Alright, so solutions are true homogeneous mixtures, right? Or a true homogeneous mixture is called a solution. That would be your first blank, solution. All particles are broken down into individual molecules or ions. And hopefully this link works. Cross your fingers. Alrighty, so here we have a little diagram. Right, we're looking inside here. We just have some water, and when we drop in, I think this is a sugar cube, right? The sugar does not react with the water. What actually happens is, right, it dissolves. So the water comes in and it separates the sugar molecules, and it breaks it down into its smallest little pieces, right? So the sugar is still sugar, right? It's not changing its identity. The water is still water. It's not changing its identity, but it's dissolving, and it's getting breaking down into such small parts that we cannot see it, right? And this is what happens with a solution. Awesome. Glad that worked. All right. And since our molecules and ions are so incredibly small in a beam of light, or so incredibly small in a solution, a beam of light is going to pass right through it. So if I shined a laser pointer through a solution, you would not see the path of the laser when it goes through the liquid. You would just see the light attached to the laser pointer and then the light on the wall. All right, and you'll see why that is important later. Alrighty, so solutions are made with substances called a solute, and that solute dissolves in a solvent. And I would want to put a star next to those two terms. Water often dissolves many things, so we call water the universal solvent. You might do this at home. So I know your parents or guardians might ask you to do the dishes, but I bet sometimes when you have some food, you just take it to the sink and fill it up with some water. That way it's easier to clean later. So what you are doing is you're actually dissolving some of the sugar or salt crystals that are connecting to your bowl or cup, making it easier for it to clean later. Some examples of our solutions would be soda, iced tea, lemonade, or sugar water. All right, these are all things that look uniform throughout. If we, even if we use a microscope, we would not be able to see, right, different clumps or pieces in there. All right, our next type of mixture is going to be a colloid. Now, solutions have the smallest particles, right, in our mixtures, while colloids have the next smallest. They're still very, very small, just not as small as a solution. All right, so colloids break down into small clumps of molecules, but not into the individual molecules like we saw with the sugar water little demo that I played in the last video. All right, so these particle sizes or clumps are very small, between 5 to 200 nanometers. Right, still too small to be seen with your eye or even a typical microscope. Now, if we did have a super powerful like electron microscope, we would be able to see these small clumps. But just with like the microscope you would see in your biology lab, we would not be able to see them. Right? Again, still larger than the solution particles. And some examples of colloids would be mayonnaise, jello, fog when you're outside, butter, and whipped cream. Right? The dust in your living room is an example of a colloid, and we'll show you an example in a second. Now the big thing to remember about colloids is that they display the Tyndall effect. All right, so with the Tyndall effect, colloids will scatter a beam of light when it passes through. So one good example would be light reflecting off the dust in the air. If you've ever tried to watch TV during like a bright day, and the light coming through the window is kind of making all the dust block your view of the TV. Right there's the Tyndall effect in action. Now I have some other examples for you. Oh, too far. Here we go. These are my friends at the Big Bang Theory. They're playing a little game of chess. It's a special game of chess. Now I'm not sure that you can hear the volume. They make some funny sounds. But what they need to do,
Queen's Bishop 5.
In order,
Oh, very nice. What's Leonard going to do?
You'll see in a second.
Does he give up the pawn or does he give up the position? Let's find out. Leonard, ready? Ready. Go.
so what Leonard has to do in order to see the laser beams is he has to create a colloid in the air around him. So by spraying some dust in the air, he's putting some very small particles in the air that's reflecting the light so that he can see. If you've ever watched a spy movie and they were not spraying anything in the air, then it was not scientifically accurate.
Damn it, I slipped.
Alrighty. So I don't think you were able to hear their volume, but hopefully you heard me narrate through that. I have a little spray bottle that we can do in class to show a little example if you remind me. So if we were shining a laser pointer through a colloid, we can see that light travel through. Right? So if it was a liquid colloid, we would be able to see it travel through the liquid. If it's something like the gas around us with some dust particles like we just saw in the video, right, we could still see that laser beam travel through. All right, and here's an example of a solution. We can't see the path of the laser, while we have a colloid on the right where we can. Right, in the solution, right, true solution, the particles are not large enough to reflect or bounce off that, make that light bounce off, while in the colloid it is. All right, and lastly we have suspensions. Now suspensions will be one little hiccup we have with the Tyndall effect. So if you're just shining the laser pointer through the top part of a suspension like we have here, you would be able to see the laser pointer. But if we're going through, if we shake up the suspension, right, these larger particles will block it. Right? And that leads us to our first blank. These particles in a suspension are the largest of our mixture types. They're large enough to be separated by a filter. Whether that's filter paper like we use in the chemistry lab, coffee filter paper, or something like a colander that you use in the kitchen. And these large particles will fall to the bottom. As you can see in our picture here of these different salad dressings, all of the large spices fell to the bottom. And some examples of suspensions would be paint or salad dressing. All right, so just to run through this one more time here, this is a very important diagram. So we can categorize all forms of matter, right, as either a pure substance or a mixture. We've talked already about elements and compounds, right? These are my pure substances. Elements is one atom, or one type of atom, right? We can have diatomic elements. And compound is two or more different types of atoms chemically bonded together. Now we just covered mixtures. We have homogeneous mixtures. A true homogeneous mixture would be a solution. And then when we get to our heterogeneous mixtures, we have colloids and suspensions. Remember, colloids look homogeneous, but truly are heterogeneous. And suspensions look heterogeneous, just like they are. Alrighty. And then one last demo that I'm probably going to do in class, but just to give you a heads up. So if we're putting together iron and sulfur, if we just mix those elements together, we can separate them easily with a magnet because the iron is going to stay magnetic. Now, if we put iron and sulfur in a test tube and we heat it up, the iron and the sulfur chemically combine together. And then we can tell that it has changed because its properties change. It is no longer magnetic. It's something that we call fool's gold. It's something that you may have collected when you were a little kid. So we'll do that when I get back in the classroom with you guys. All right, have a great rest of your day. See ya.